Hi students, it's Dr. Marks and we're going to wrap up our discussion of nonlinearities in regression with one more good example. So let's get started. Quick review. We've already talked about the idea that some variables have a nonlinear relationship. You see here in this picture clearly a nonlinear relationship because instead of a straight line being fitted, it's really more of an arc shaped, right? So not a straight line. What's this example? We've already reviewed this one, but this is looking at jawbone length versus age. We see age on the horizontal axis, we see jawbone length on the vertical axis, and basically what we're saying is that as our age increases, our jawbone gets longer. Let's think about just that first part because this is the non-quadratic portion. It basically says there's a positive relationship between age and jawbone. And we see that in the picture, right? It is upward sloping, but it's not a straight line. What we're seeing is a diminishing effect, right? The jawbone's getting longer and longer and longer, but more and more and more slowly. So this increase is increasing at a diminishing rate. Adds a little bit, but then adds a little bit less, then adds a little bit less. So that's the quadratic or squared term. Now, remember that when we're doing regression and we want to add a nonlinearity, we need to use the quadratic form, and that's going to help us test for nonlinear effects. That requires us to have our variable, here I'm just using x, but remember it's got to appear in your model twice. X not squared captures is it upward sloping or downward sloping. X squared is that quadratic portion. This is where we're capturing the part about it not being a straight line. Is it increasing at an increasing rate? Is it increasing at a decreasing rate? Again, if x is negative, then it's decreasing. It could be decreasing at an increasing rate or decreasing at a decreasing rate. So we covered that in part one. Hopefully that is meaningful to you. But again, both terms have to be there. That squared term is what's capturing the increasing or decreasing marginal effects. So keep in mind, 4 choices: increasing at an increasing rate, increasing at a decreasing rate, or if x is negative, it's decreasing at an increasing rate. And the last one, decreasing at a decreasing rate. So that's review. Hopefully you understand that. If not, go back to that first lecture because we do that very methodically. We look at a lot of pictures. So my second example here we're going to look at, the one that's new for this lecture, is a wage study. And wage here is a function of experience. Now in this example, they're calling experience tenure. What's your tenure at your university? What's your tenure at your current employer, for example? Notice that you see tenure appear twice. The nomenclature is a little weird. So tenure, the first red box, is around just that linear part, right? That's like the x variable I had in the previous graph where it's not squared. But then right below it, you see a different version of tenure. That's tenure multiplied by tenure, or tenure squared, the quadratic. Don't worry about why it's called C period tenure hashtag. Doesn't really matter. That has more to do with the programming language or the way that they named the variable. But it could have just been tenure SQ. If this was my work, I'd probably just name it tenure SQ for tenure squared. All right, so we see that tenure enters both linearly and in the quadratic form. And don't forget, you have to have both. Now, if we look at the first variable, tenure, not the squared part, but just the tenure, we see that it is significant, right? How do we know that? Everyone look at the p-value. P-value of 0.000 tells us that it's significant at 99.9% level of confidence, right? So highly significant. And look at the coefficient, 0.277, it's positive, right? So everyone agree with my first statement? Tenure is significant and positive. Well, that makes sense, right? More experience usually means higher wage. We would expect that to have a positive coefficient, and it's not surprising that it's significant, right? All right. How do we interpret this? Again, just for a quick review. for an additional year of experience, and remember, you don't want to say for 1 unit of, you want to say for an additional year, be clear about what your units are, for an additional year of experience, our wage increases, and this must be hourly wage, increases by 0.277. Remember, this is dollars. Wages are in dollars, so 0.277 in dollars is 27.7 cents. So clearly, this is some kind of hourly wage. Now, we also have tenure squared, which is in that second red box with the weird nomenclature. But that's essentially tenure multiplied by tenure, or tenure squared. So in your Excel spreadsheet, you need to calculate tenure squared, and you can do that in 2 different ways. One easy way is tenure multiplied by tenure. All right. Now we see this variable is significant at just about the 95% level, right? It's just a hair off, 0.051. It's probably more accurate for me to say at the 94% level of confidence. So to be a little more precise, but we do see that it's significant, but it's negative. All right, so let's make sure we understand what's going on here. Tenure is positive, but the quadratic is negative. So what does this tell us? Tenure makes wages go up, but the squared part says that is making it go down. Okay, so what we're saying here is that the slope on tenure reduces by 7 cents for each additional year. That while tenure or experience makes wages go up for each additional year, it's 7 cents smaller. All right, does that make sense to everyone? Think about that again. So tenure says it's positive. Tenure means that experience is making wages go up. That's the first part. But the quadratic term is negative, which says, okay, while tenure makes wages go up, it's a diminishing effect, right? It's a diminishing effect. It's a decreasing effect. And think about that. In the real world, that's probably true. That you guys are probably getting really great raises when you're young. Then you get to my age, and while 1 year more of experience makes my salary go up, my guess is it's probably a little less and a little less and a little less each year. All right. So if we were thinking about the picture of what this looks like, we're getting something that's fitted to more of a curve. It's upward sloping, right? Job tenure is on the horizontal axis, and our vertical axis is capturing the salary. So these are kind of predictions with your confidence intervals, but you get the idea. The relationship isn't linear. It's going up as you have more experience. Your salary's going up, but it goes up a little less and a little less and a little less. In this example, it actually turns out to be slightly backward bending. So again, initially you get a higher wage as you get more experience. We see that. But the gain that you're getting gets smaller and smaller and smaller. And specifically, using the data and the results we just looked at, gets 7 cents smaller. Eventually here on this graph, the net effect is negative, right? So we have that quadratic term taking a bite out of the increase in your wage. And at some point, that bite means you're actually seeing a decrease in wage. Now, that doesn't mean literally for one person. Remember, this is a data set of a whole bunch of people. But we could have this backward bending result as we see here. And in this example, where does that backward bend occur? It occurs at around 20 years of experience. So that's what the data is telling us. And again, remember, we're not saying literally that this is one person, right? It's not saying you get old and they cut your wages, because they probably can't do that. We're just saying the data set suggests when we look across a whole lot of people, we see this kind of relationship. All right. Now, again, remember, what if that squared term is not significant? Well, that means quadratic is not the right fit. Does it mean I need to drop that from my regression? No, not necessarily. It just tells me that maybe the real relationship is indeed linear after all. So again, let's recap. We've talked about the specification issue related to nonlinearity. What do you do if you think there might be a non-linear relationship? And there's lots of places where we might expect nonlinearity. We've said we have to model that with a quadratic function. Remember, this requires both the linear and the quadratic form of the variable to be in the model together. And this is what people forget. You can't just drop that first part in lieu of having only the quadratic part. You've got to have them both. So let me know if you have any questions. I appreciate you listening and have a wonderful day.